seminar. So today we have the pleasure of having Pierre Botteron to give us a talk about non-local boxes and computational complexity. So brief introduction to our speaker today. So he is a second-year PhD student in quantum information theory. He is in, I guess the affiliation is in Toulouse and Ottawa at the same time. Yeah. And so basically, his advisory team is composed of Professor Anne Broadbent, who is in Ottawa, and Ion Nikita in Toulouse, and Clement Pellegrini, I guess also in Toulouse. Yeah.
Mhm.
So they're interested in the question basically like, is quantum mechanics sort of the appropriate theory to describe the world? And the way that they tackle this problem is to consider what we call no signaling correlations that he will try to introduce to us today. And basically saying that things that are no signaling but not quantum will be in some sense very unlikely. And the way that they try to establish this is through some argument involving communication complexity. So you can, the floor is yours, Pierre.
Yeah, thank you for the very nice introduction. Thank you for the invitation. So as you said, I will talk about non-local boxes and communication complexity today. So I will introduce the two notions, and after introducing the notions, I will try to explain the three works that we had. So mainly the first one, and then quickly the two other ones. But first, let me give you a motivation. So first, motivation of why we do it. Motivation. So the goal behind this work is to find it's to combine several principles. Several principles to rule out the set of quantum correlations so this set we denote it by Q from the sets of non-signaling correlations from the set of non-signaling correlations which we denote the NS by NS. So I will explain what is a non-signaling correlation. And here, as you said, we will mainly focus on one principle, which is the principle of communication complexity. Communication complexity. So this one as well, I will explain what it means. I will write CC all over the presentation. And what you need to remember is that a collapse of communication complexity seems to be impossible in nature. Seems impossible in nature. So it would be very surprising to find something that implies a collapse of communication complexity. And a remark that you need to remember as well is that no quantum correlation can imply a collapse of communication complexity, but some non-signaling correlations imply a collapse. So those non-signaling correlations that imply a collapse of communication complexity seem to be impossible in nature, and I will explain why later. So the question for today is the following one. So what are all the non-signaling correlations that collapse communication complexity. So this is why now I need to give you some background on those notions. So background. Oh, by the way, if you have any question, don't hesitate to interrupt me at any time.
Yeah, yes. So I would like to, could you elaborate what do you mean by collapse? For example, when you say correlation collapse, communication complexity, what does collapse means in this?
So I will define what is communication complexity, and I will explain what it collapse it.
Okay.
So
Good. Sorry.
Yeah, it's you will. I hope you will understand it at this time. If you don't understand it, please ask me again. But I will precisely.
Okay.
Thank you for the question. So the background, first, I want to define something very basic, which is the CHSH game. CHSH game. So it's a famous and easy game. This game involves two players. So we call them Alice and Bob. Alice and Bob. Okay, well. So they are space-like separated, meaning that they cannot communicate. So there is a kind of a wall between them. A referee arrives. So, oh no, it's not beautiful. Okay. A referee arrives and he provides Alice and Bob with some bits that we will call X for Alice and Y for Bob. And in return, they need to answer some bits A and B. So A for Alice and B for Bob. And so in this game, we say that Alice and Bob win the game. Alice and Bob win if and only if the sum mod 2 of A and B is equal to the product X times Y. As you can see, it's not so easy to win the game because Alice knows X, she doesn't know Y, so and the same for Bob, he knows Y, but he doesn't know X, so they don't know the product, and they need to collaborate to have the sum equal to the product. So they can do different types of strategies. The most basic type is the deterministic type. So deterministic strategies. In this type of strategy, the output A is a deterministic function of the input X, and similarly, the output B is a deterministic function of the input Y. For example, you can take A equals 0 all the time and B equals 0 all the time. So you have the sum here that is always 0, and the product X times Y is equal to 0 when X equals 0 or Y equals 0, which happens 3 times out of 4. So you can see that you can reach the 75 winning probability quite easily, and actually it's the best winning probability with deterministic strategies. So you can win up to 75%. But now imagine that they have access to what we called shared randomness. So it's a classical strategies. In that type of strategies, they have, for example, they can have access to shared dice. So the referee rolls the dice, they see the result of the dice, and both of them can use the result of the same dice to correlate the answers. So we might think that they can do better, but actually it's possible to show that the winning probability, the best winning probability remains the same, so 75%. And the proof is based on convexity because classical strategies are convex combinations of deterministic strategies. But now we can introduce, they can use a more general type of strategy, which are quantum strategies. So in that case, they don't have a dice, but they have something more powerful, which is, for example, a quantum entangled state. So one particle for Alice, one particle for Bob, and this is entangled. What they can do is to choose a basis in which they do a measurement. So based on X, Alice can choose a measurement, and from this measurement, she obtains a classical bit, spin up or spin down or something else. And Bob can do the same thing based on Y. He can choose a basis for measurement, and he obtains some classical information. And from the classical information they get from the measurements, they can produce A and B. And it's possible to show that in that scenario, the best winning probability is strictly better. It's cos square of pi over 8, which is also 1 over 2 plus 1 over 2 square root of 2, which is about 85%. Okay, and so the last type of strategy that I want to introduce today is the non-signaling one, that we call as well non-local boxes, which was in the title. So non-signaling strategies. So instead of having a quantum state, they have a sort of black box for which we don't know what happens inside. So it's a black box that we call non-local box. This box has two inputs and two outputs, one for Alice, one for Bob. And so imagine there is a quantum state inside, but we don't know what kind of state there is. It might be something beyond quantum theory. We just look at the statistic behavior. So Alice inputs something, some classical information, Bob as well, and they receive some classical information. And from the big A and big B, they can produce small a and small b. If they have a very good non-local box, we can show that they can reach the winning probability of 100%. So this is achieved with the Pierre box that I will show you later. But let me give you a more precise definition of what is a non-local box. So we can call it P. So it's any P such that, so you want that P of AB given XY is non-negative, and you want that the sum over AB of PAB given XY is 1. So those two conditions make P being a probability distribution, a conditional probability distribution. And you want as well that the marginals are well defined. So if you take the sum over A only, you have that the sum of PAB XY is equal to the sum over A of PAB given x tilde prime for any x and x tilde. So it means that it does not depend on x. So we can call this thing P of B given y. And the last thing we want is that you have the same thing for the sum on B. So same for the sum on B. And these are the 4 constraints that you have for a non-signaling strategy. So if you want to have the physical interpretation of this thing, it's that you don't have any signal from the input X to the output B. and you don't have any signal from the input Y to the output B, to the output A. This is why we call them non-signaling. So I will put this stuff there. Okay. Okay, so let me give you some examples, some famous examples of non-local boxes. Examples of, so non-local boxes, we can write it NLB, like this. So first, I will give you some local examples of local boxes with the local strategies. So if I write it like this, local boxes. For example, you can take the box that is called SR. This one stands for shared randomness. So of AB given XY. This one is defined with a Dirac mass, and you want that the outputs are always equal. And you put a weight 1/2 so that the sum is equal to 1 when you take the sum over A and B. So this one was the same as the when you roll the dice, you want that Alice and Bob see the same results, so they want to have the same outputs of the non-local box. Another example is the fully mixed box. So this one will output couples AB that are fully random, so and uniformly random. So you put 1/4. These are local boxes. So now let me give you examples of an example of quantum box. Quantum box. For example, you can take the Bell state. So 0, 0 plus 1, 1. And you can take POVMs. So you can call it like this. Sorry. FB given Y. So POVMs, so projector operator valued measurements. And if you consider P of AB given XY of the following form, then it will be quantum. So you take the measurement of phi in the base using the POVMs. Up. Okay, maybe I should write it smaller so that it fits. Okay, like this. So this thing is a quantum box because it comes from quantum mechanics. And now I want to show you examples. An example of non-signaling box. So which is the more general kind of box. The most famous one is the Pierre box. So Pierre stands for the others. So named after Popescu and Rohrlich. And this one is defined with a Dirac mass as well. You want that the sum mod 2 of the outputs is equal to the product of the input. You put 1/2 in front to have that the sum over AB is equal to 1. And you can see that this non-local box with this condition is precisely designed to perfectly win the CHSH game because we have the same condition here. So this Pierre box is the one achieving the 100% winning probability for the non-signaling strategies. And you can verify that this definition satisfies the 4 conditions. So it's non-negative, it sums to 1, and the marginals are well defined. So, okay, so these are non-local boxes. And now I want to define what is communication complexity. Communication complexity. So I will write it CC. Okay, I put it in blue. So maybe the stuff before was not so new for you, but this stuff might be new. So I will try to explain as well as I can the details. You can view communication complexity as a game, as before, but it's a different game. So again, you have Alice and Bob. Oh, come on. Okay, and you have the referee. So at the beginning of the game, they are not yet space-like separated. A referee arrives. Okay, oh, I will need some room above. The referee arrives, and he defines a function f with 2 strings as input, so 1 string of size n and 1 string of size m, and a bit as output. And what he does is it's that he will provide this function to Alice and to Bob before the game starts. So he gives f to Alice and f to Bob. So they can still communicate at this time of the game, but then they are space-like separated. So I'll put like a big one. Okay, so there is a wall then between them. And then what do they need to do is that the rule of the game is that Bob can send 1 bit of communication to Alice. Oh, sorry, before sending anything, they receive some strings. So Alice receives a string big X of size n, and Bob receives a string big Y of size m. And what Bob is allowed to do is to send 1 bit of communication, so B. And we want Alice to send 1 answer to the referee that we call A, which is as well a bit. And we say that Alice and Bob win the game. Alice and Bob win the game if and only if the answer of Alice is equal to f of xy. So as you can see, it's not so easy to win the game because Alice completely knows x and f, but Bob needs to turn the big string of size n into a small, into only 1 bit, a 1-bit message. So we say that a function is trivial, definition, I'll write it there. We say that f is, f is trivial in the sense of communication complexity. If Alice and Bob can perfectly win the game. And this needs to hold for any x and for any y. So I repeat, so the referee provides a function and 2 strings to Alice and Bob, and they win if and only if Alice can evaluate the function with only 1 bit of communication between Alice and Bob. I will give you some examples of trivial functions and of non-trivial functions. Example. let's consider the easy case where n equals m equals 2. So the size of the inputs are very small. So you can write the strings explicitly like this and this. So first example we can consider is the following one, is the sum of the inputs, x1 plus y1 plus x2 plus y2 plus 1. And I claim that this function is trivial in the sense that I defined before. So we need to show, and I will show it. So we need to show that with only one bit of communication, Alice can evaluate this function for any x and y. How do you do? So when Bob receives the string y, he can compute y1 plus y2. He calls the result b that he sends to Alice, which is only a bit, and Alice can compute x1 plus x2 plus 1 plus the bit b from Bob, and she knows the value of the function f for any x and y with only one bit of communication. So this shows that this function is trivial. Another example of trivial function is the following one. If you take the products x1 times x2 plus y1 times y2, this one is trivial as well for almost the same reason. So when Bob receives the string y, he can compute y1 times y2. This is a bit. He can send this bit to Alice, and Alice can compute x1 times x2 plus the bit b from Bob, and she knows the evaluation of the function for any x and y. So now we might think of an example of non-trivial function, still with n equals 2 and m equals 2. It might not be obvious, but there is one. There is, like, you can find several examples, but for example, this one. You can take the inner product function, x1 times y1 plus x2 times y2. So you can see that, and I claim that this one is not trivial. Not trivial. So you cannot compute it with only one bit of communication. Why is it so difficult? It's because you mix Alice information and Bob information twice. So if you make the computations, it's possible to show that you need at least 2 bits of communication to evaluate this function. And which are the bits? It's simply y1 and y2. So Bob needs to send the 2 of them or something like some equivalent information so that Alice can compute this function perfectly. So this function cannot be computed with only one bit of communication. Okay, so this is the definition of trivial function. And now I want to define what is the collapse of communication complexity. So to do it, I need to draw again a non-local box. Oh, come on. Okay. So imagine Alice and Bob have a non-local box that we call P with some inputs and some outputs. They can use it to help them to compute the value of the function to win the game. So we say definition the non-local box P is collapsing communication complexity. Collapsing communication complexity if there exists some probability small p strictly bigger than 1/2 such that for all function f no, sorry. So with arbitrary input size, So every function like this, such that every function like this is trivial with probability bigger than or equal to p. So it means they can make mistakes in evaluating this function f, but they shouldn't do too many mistakes. So they want to have only one bit of communication for any function with any input size. So this is the remark that I want to highlight, and that I said it in the beginning, in the introduction. It's that a collapse, such a collapse, seems impossible in nature. So let me explain why. Imagine the opposite. Imagine that.
Sorry, can I interrupt just to clarify something? Okay, so communication complexity will be a property of the Boolean function f for arbitrary communication strategy between Alice and Bob that has at most one bit of communication, right? And then I guess you're taking like the minimum amount would define the communication complexity. Is that correct? Okay.
Yes.
So now, but now you're collapsing is a property of the non-local box or arbitrary Boolean function, but then it will be only for communication strategies that use the box.
Yes, exactly.
Okay. Just
So,
making sure that
yeah, if they don't use the box, they cannot collapse communication complexity. It's possible to show that they cannot. And so now if they use the box, they might be able to collapse communication complexity in some cases. So thank you for the clarification. For example, if they have access to a Pierre box, the one that I defined before, they can collapse communication complexity. They need several copies of this box. They need to use it several times, but they can compute any Boolean function with arbitrary entry size with only one bit of classical communication.
Oh, okay. Yeah, I mean, yeah, I don't know if you mentioned it. So they can have as many copies of the boxes as they need. So the boxes are free in some sense.
Yes, exactly. Which is not very realistic, but it's the principle. Yeah.
Yeah. Okay. Yeah. Thank you.
So this collapse seems to be impossible in nature because you see the input of Bob can be arbitrarily large, and Bob needs to compress the information in only one bit of communication. So he needs to compress m bits into one bit so that Alice can evaluate the function with high probability. This is why this seems to be impossible in nature. So if something here is powerful enough so that only one bit of communication is sufficient, then this box seems to be impossible in nature. So as an example, I said that the Pierre box is collapsing, so I will write it. Pierre is collapsing. So it means, as a consequence, that it seems to be impossible to exist in nature. So it seems to be impossible to win with 100% of probability at the CHSH game. And on the opposite, if you take any box that is local or quantum, for example, we saw SR, we saw I, and we saw the one with the Bell state. So it was this thing. Then P does not collapse communication complexity. So we want to find as many non-local boxes as possible that collapse communication complexity the same way as Pierre does. So this is the purpose of our work. Is there any question before I go to the results?
I'm good, thank you.
Okay, thank you. So then I will move to the results that we had about that. Okay, so results. Put it in red. Okay. So I will try to present 3 results, but I will emphasize the first one more. So result 1. Maybe I can copy paste the reference at the beginning. So it was this one. Copy. Paste. Okay. We don't need this thing. Okay. So, oh yeah, and I wanted to show you a picture of the people that were involved in this work. So it's Anne Broadbent and Marc-Olivier Proux, for which I don't have any pictures, so I had to make a drawing. I had to use my drawing skills to represent him as faithfully as possible. So in this work,
I'm sure it looks just like him.
Yeah, you will recognize him when you meet him. So in these first results, here is, so I made a drawing as well to present the results. It's this drawing here. So you see in blue, I've made the non-signaling set. Inside there is the quantum set in red, and inside there is the classical set L in green. And in this result, so theorem, we found the equation of a certain ellipse. And if you go outside of this ellipse, you will have collapsing non-local boxes. And I want to mention that the Pierre box is at the top of the drawing. So the theorem is that I will not give you the equation because it's a bit complicated, but every non-local box that is in this striped area is collapsing communication complexity. Okay, so let me give you the sketch of the proof of this result, and I hope you will understand it. So I'll write it in black. Sketch. It's quite, I find it quite interesting, but it's a bit biased. So you introduce a function f, any function f with Boolean strings as input and a bit as output. You consider strings, so x and y, as in the game before. And we want to show that Alice can evaluate the function f applied to x and y with only one bit of communication and with a high probability, bounded away from 1/2. So we'll do 5 steps. First step, so let me see my notes. Okay, so first step is to find a protocol that we call P0 of f. So this protocol depends on f, and this protocol needs to win at guessing. So a bit A for Alice and a bit B for Bob, such that we have A plus B equals f of xy with no communication and with probability P0 of f bigger than 1/2. So I want to mention that this protocol is not from us. It's from Gilles Brassard, Burman, et al. In PRL 96 25041 2006. This protocol is not very difficult, but and if you want to have the details, I can give you the details, but I think it's better to keep it for the end if we have time, or if you have questions, I can explain it. But just understand that we can find such a protocol P0 that can compute distantly this function with no communication and with probability that depends on f bigger than 1/2. Okay, so next, the second step is to build a new protocol that we will call P1. So you repeat P0 of f 3 times. So we get 3 guesses. Sorry, 3 guesses for f of x. So you have a first guess is a1 plus b1, you have a2 plus b2, you have a3 plus b3, because you repeat it 3 times. So you obtain a, b, and c 3 times, a and b 3 times. And what you want to know is what is the most frequent value, so that you can maybe increase the winning probability at guessing the right value of f. So what they do is we compute the majority function of the 3 results. What is the majority function? It outputs the most appearing bit in the input. The most appearing bit in the inputs. So let me give you examples if you want, if you need it. So if the inputs are 0, 1, 1, for example, the output of the majority function will be 1, because you have 2 ones. If you have 0, 0, 0, you will obtain 0. If you have 0, 0, 1, you will obtain 0. So this is to reduce the noise, to increase the winning probability from P0 to P1. So to compute this this majority function, we need to use 2 copies of the non-local box P. It's a bit technical, so I don't have enough time to explain how to use them, but what you might understand is that a non-local box is helpful to turn a product into a sum. So every time you see a product, you can turn it into a sum with some noise using a non-local box. This is what we do, and so at the end of the day, this defines a protocol P1, defines a protocol P1 of f that wins at guessing, so some bits a and b, such that, as before, a plus b is equal to x f of xy, with probability P1 of f that will be strictly bigger than P0, and with no communication. Okay. So now you know how to go from P0 to P1. You can do the same from P1 to P2, from P2 to P3, so on and so forth. So for all k, you can do the same. How can I say? Sorry. Define pk plus 1 of f from pk of f. So you have a sequence of protocols, and the winning probabilities, they are getting better and better. So we have pk plus 1 of f better than pk of f, better than the previous ones, better than p1, better than p0, which was greater than 1/2. And everything is with no communication. It's important because we count the communication bits. Communication. Okay, the fourth step out of 5 now consisting in doing some mathematical analysis. So we prove, we study the limit of this sequence of pk's, and we prove that the sequence pk of f is converging to some p star for k going to the infinite, which is bigger than 1/2. And to do so, we use a fixed point theorem. And what is very important is that P star does not depend on F. Does not depend on F, neither on X and Y. So it does not depend on anything from the function. This is important because in the definition of collapse of communication complexity, you want to find there exists a probability P bigger than 1/2 such that for any function, blah, blah, blah. So the probability P cannot depend on the function and neither on the inputs. Okay. And now, last step of the proof. Hence, so there exists P that we will take to be P star plus 1/2 divided by 2. So this is my small p, such that for all f, so the Boolean functions, and for all f, there will be a k big enough such that we will go above the threshold. So such that pk of f will be bigger than p, and this p, sorry, is bigger than 1/2. So this thing, I can put it there actually. Okay. And maybe I want to highlight this thing is that, or maybe this one, independent of f, x, y. Okay. Okay, and then what we can do now, so in this k, so we fix this k. So we have a protocol pk of f. Alice and Bob produce some bits a and b such that a plus b is equal to f of xy with probability pk of f that is bigger than p. So Bob can send 1 bit of communication, so he can send the small b, to Alice, and Alice knows f of xy with probability pk of f bigger than p, which is independent of f. Hence, there is a collapse of communication complexity. So this is the idea of the proof. If you have any question, I might have been a bit fast on some points. And this proves that, so the black area in my drawing, these are the non-local boxes that we used in the point 2 here. I use a non-local box here. So this box, it's in the stripped area of the drawing. So this box needs to have some specific properties to not to reduce too much the winning probability. Okay, if there is no question, I just want to mention very briefly 2 other results that we had concerning non-local boxes and communication complexity. So result 2. Maybe again I can copy paste the reference. So this is this one. Okay. Okay, and I can show you the faces of the people. So it's again N Broadbent. The first one, Reda Shaibi, and Yon Nikita, and Clément Pellegrini. And yeah, so they worked with me. And so what we did, I think I have a picture. Yes, I have this one. Okay. So what we did in this work is considering a wiring. So I write it there. A wiring W. So imagine you have 2 copies of a box. You have a box P here, a box Q, and you want to produce a new box out of those 2 boxes. So what you can do is to plug the inputs to the outputs to the input. So you can connect them to produce a new box, the big box. The new box, we call it P box time Q, subscript W, because it's using this specific wiring. And you can see that this wiring is quite strange, because here you go linearly from the top to the bottom on Alice's side, but on Bob's side, you begin with the second box, and then you go to the first box, and then you output the thing. But still, this type of wiring can be used in reality. So this is like an example of wiring. It defines a notion of product between non-local boxes. So you can do P times P, P times P times P, so on and so forth. So you have an algebraic point of view on composition of boxes. And what you can do is then to produce the orbit of a box. So you start from a box here, P, in NS, and what, here, and then you compute P times P here, and then you compute P times P times P, and then P times P times P, and you compute many possible combination of products of P. And as the product is non-associative, you can do P times P times P or P times P times P. So this is why you have like many layers. And what is very interesting in this point of view is that if you start from a box here, you can distill the correlation, so you can make it rise until some threshold. So the dark green area is a collapsing area. Or we can use the result before, like the ellipse that we had. So if you're above a certain ellipse, then you collapse communication complexity as the result 1. And if you go above with the orbit, then it means that the starting box is collapsing communication complexity as well, because you can produce a finite protocol to collapse communication complexity. So as a consequence, you have an algorithm to compute what non-local boxes are collapsing. And we deduced that many sets of non-local boxes are collapsing. So I give you some examples there. If you take this triangle of non-local boxes, any non-local box in this triangle will be collapsing communication complexity using this wiring, and the same for many other sets of boxes. And very, very quickly, I want to mention one last result that we had. It's about a different game. It's a very recent result. Results, sorry, results 3. I will copy paste the reference. Copy. It's online as well. Maybe I can show you a picture of the collaborator. It's Moritz Weber from Germany. And in this work, so instead of considering the CHSH game, we replace the CHSH game by a different game. So we tried to use the graph isomorphism game. We tried to use the graph coloring game as well. Coloring game. And as well the vertex distance game. Because you remember, I said that if you have a perfect box at the CHSH game, which is the Pierre box, you collapse communication complexity. So the question is that if you have a perfect strategy for those games, do you collapse communication complexity as well? And the result is yes, in some cases, because from a perfect strategy at those games, you can produce a Pierre box. So if you have a perfect strategy, for example, the graph isomorphism game, you can pre-process and post-process the information to generate a Pierre box. So here is the pre-processing and the post-processing. And so if you are able to generate the Pierre box, then it means that you collapse communication complexity. So as well for those games, it's not only for the CHSH game, it's as well for different games that if you win perfectly the game, then you have a collapse of communication complexity. Okay, and that being said, I just want to thank you for your attention. Thank you for your attention.
Okay, thank you very much. That was a very wonderful and interesting talk. And yeah, so let me just see if anyone in the audience has questions. So you can, I guess you can just unmute yourself and ask now.
Thank you for the wonderful talk. So I just want to ask the conceptual question. So if you have the collapse of communication complexity, its implication for the quantum correlation, what's the implication for the correlation? It means there is no correlation or perfect correlation. What's the implication?
If I well understood the question, so for quantum correlation, you cannot collapse communication complexity. So it's not possible. And it's convenient because we know that you can produce quantum correlations in reality with experimentations and things like this. So it does not contradict quantum theory. But now if you have a perfect strategy at the CHSH game, you collapse communication complexity. So this does not exist in reality. Does it answer your question?
You try to clarify which situation does not exist in nature. So that's you are extending the boundary. Basically, this is the purpose of non-sequencing approach. I see.
So yeah, so we know that this area in black is collapsing here as well, and we can do by symmetry the same thing here. But in between, so here in orange, here, we don't know if you have a collapse of communication complexity or not. So the question is still open. That still some boxes we don't know if they collapse or not communication complexity. So it leaves some room for a more general theory than quantum theory that is maybe plausible in the sense of communication complexity.
I see. Thank you.
I guess Yongchen, you have a question?
How do you know?
Because you're unmuted.
Right. Hi, thanks very much for this interesting talk. So just wanted to clarify this. So are you saying that as far as trivializing communication complexity is concerned, your work has basically done everything that needs to be done in this scenario?
No.
In terms of excluding non-local correlations beyond quantum?
Not everything is done. There remains the orange area is still to be studied. We still need to study this orange area. It's still open, but we made some advances, but it's not yet finished.
But what is there that you could still consider? Because actually, it seems like the problem setting they've considered is already pretty general, right? What else could you put as new ingredients in order to expand that region of exclusion?
We don't know. We don't know, but like what would be nice is to prove that this orange area is not collapsing or collapsing, but we don't have any proof yet. And it seems to be quite difficult, as you said, because there were many attempts in doing it, but
I guess maybe okay. I think maybe this is the thing. So you have considered specific type of protocols, right? In order to do your computations, there could be, let's say, other ways, different protocols that are maybe more suited for ruling out some other regions in the space. Is that a possibility?
Yes, definitely.
I see. Okay.
As well, you can use a different principle that communication complexity. At the beginning, I said we need to combine several principles. Many people work on information causality or different principle, like macroscopic thing, I don't remember. And so you can combine the principle to rule out as many non-local boxes as you want.
Yeah, sure. But they were using different principles. So I was asking, is this already the end in terms of using the principle of non-trivial communication complexity? But I guess even for this question, it is not the end yet, because there can be other protocols that you can consider.
Yeah.
Okay.
Exactly. Yeah.
Right. Thanks.
I mean, just to sort of add to it, because earlier you said that so in your protocol, you have something where you wanted, I guess, like some P star, where you wanted it to be independent of F. But strictly speaking, it could depend on F as long as it's sort of still like has the property that you want. Of course, it would make the proof sort of very ugly, because now you have some proof that's sort of like for different F, you kind of have to prove it differently. But strictly speaking, that might be possible if you have like some very convoluted kind of protocol, right? But probably you don't want to prove things in that way.
Yeah, that's right. But at the end of the day, you want to have something independent of F because of the definition. You want to have some P that does not depend on F, such that for every F, you have that a trivial thing with probability bigger than P. So you have something bounded away from 1/2. So you can consider a sequence of probabilities depending on F, but the limits when the size of the inputs of F tend to infinity should be bounded away from 1/2, which is quite difficult to show. Yeah. But I see, yeah,
so just wanted to check if there's other people with questions. Otherwise, I will ask something.
I think I have perhaps two
Okay.
questions. So the first is about the collapse of communication complexity. So I was wondering why do you label as a collapse of the communication complexity? Because the scenario that you showed us apparently is like a one-way communication with only one bit of communication, but there's like different scenarios, right? So I was wondering why do you guys define like that?
Well, you can consider the two-way communication, as you said, like this.
Mm-hmm.
At the end of the day, you want, in this definition, you want only one bit of communication. So you can assume that the communication is from Bob to Alice, otherwise Alice doesn't get any new information. But there is another definition in which you want to have a finite amount of communication instead of having one bit of communication.
Yeah.
And in that scenario, we can allow them to exchange in the two ways. But
So,
like,
but wait, so your result is actually more general than you presented to us. Like you allow for a finite amount of communication, and you also allow for two-way communication, or no?
no, the result is only for this case, for this strong case. Yeah.
Okay. And the second question was about the non-local boxes. I'm not super familiar with it. And I think you mentioned something, if you go a little bit down, more. Oh, no, not so much. It's about what is possible, like in nature. And I think Jello mentioned as well that you're trying to see like if there's something that describes nature better than the quantum theory that we have. But I do have a question like about these Pierre boxes. Are they like real? Like the example that you showed seemed to be very like handmade, and like so I'm not sure. Like, are they real? Are they implementable? Like, do they exist like at all?
No, they aren't implementable because they collapse communication complexity. So if they were implementable, they would have like strong consequences on the way we communicate to solve function. So it's a theoretical tool, a black box, that satisfies the non-signaling principle. So it does not signal between Alice and Bob, but still it collapses communication complexity. So it's a way to show this thing cannot exist in nature.
Ah, okay.
Yeah.
So this is one way of rule out, like from the like the tools that we have, ruling out what we should like. Perhaps we shouldn't take this. Okay.
Exactly.
Okay.
Exactly. Yeah.
Okay. Thank you, and thank you for the presentation.
Thank you.
Okay, so I guess we were running a bit long, but I have just one more quick question. Because in the paper you have like this diagram where it shows that almost quantum correlations are non-collapsing. So
yes.
that means that whatever we're trying to show here will not actually give you back quantum. Because of course almost quantum is strictly larger set.
Yeah.
But is it like it's still possible that you can go all the way to almost quantum? So there's a gap, right, in the region?
There's a gap, so we don't know. And maybe you can rule out almost quantum with a different principle. So you can use information causality, for example, instead of communication complexity to rule out the almost quantum set. You see, so this is why you need to combine several principles at the end of the day.
I see.
You see, communication complexity will not be enough alone to rule out the quantum set, so you will need several principles. And almost quantum is slightly bigger. It's like there, yeah, and it's not collapsing.
Okay.
Yeah.
Okay, so I guess we can sort of end the talk here. People can still stay and sort of like ask questions if you were shy, but I will stop the recording now. And again, thank you for very clearly understandable presentation. I enjoyed it very much.
Thank you very much.